Okay, so the first speaker is Ken Sekimoto, and the title is Martingale Beyond an Expectation. Please start.
Okay, thank you, Chairman Sagawa-san. And my name is Ken Sekimoto. I'm happy to be here in Zoom. Today I'd like to talk our recent work, which is mainly done in collaboration with my young colleague, Charles Mosronka. So the Martingale in physics is an old and also new subject. This is old in the sense that it has long been used in the community of the Brownian motion and financial physics, etc. And the unbiased nature of Martingale is well fitted for the, for example, absence of arbitrage in financial physics, etc. At the same time, the Martingale is a rather new topic in physics, in the sense that the stochastic thermodynamics found its meaning as a common prototype of fluctuation theorems. It is only 10 years ago, more or less, by these authors. And nowadays we know that the Martingale is can be an intrinsic physical property more than just a tool of mathematical probability theory. So, by the way, I have been interested in what we call progressive quenching, PQ, which is the repartition of system versus external system. And by chance, we encountered another type of Martingale different from the type that has been a lot studied in the context of the fluctuation theorem. So now we see several examples in which the Martingale as an intrinsic physical property. So object of my talk today is to introduce a route to Martingale by so-called TIFR rule, or the law of total expectation, and tell you about several consequences of Martingale beyond the conditional expectation, by which the definition of Martingale is given. So first I recall what is Martingale and tell some typical Martingales. So in my talk, I'd like to introduce a notation for abbreviate the history from time 0 to t in discrete time, just to note x from 0 to t. And then the definition of Martingale is such that a stochastic process y sub t is said x 0 to t Martingale when the y sub t is determined by the history of x up to t, and the conditional expectation of this y sub t given the condition of the partial history of x up to s, where s is the prior to t, is equal to y sub s is the time prior to t. So this is a equation of function or functional of history. An example which is well known now in the stochastic thermodynamics is a Martingale by a path probability ratio. It is defined as a ratio of the two path weights. So if yt is defined as the ratio of the path weight qx from 0 to t as an object path weight to the ratio to the reference path weight p from 0 to t. And when the x process xt evolves under the path weight, reference path weight p of x from 0 to t, this process y, the ratio of the path weight, is Martingale. We can show it very simply by using the conditional probability. Here today, I'd like to introduce another type of Martingale, which is based on the TIFR rule. the basis of the Tower rule is the following. So suppose x and z are the random variable of a probability space. Then the expectation of the conditional expectation is nothing but the simple expectation without condition. Here, the external expectation on the left-hand side is about the random condition x. Similarly, if the x1, x2, and z are the random variables of a probability space, then the conditional expectation of the double conditional expectation is equal to the simple conditional expectation. These identities are based on the identity of the conditional probabilities. We often evoke the geometrical interpretation of such equality as a law of three normals for an orthogonal projection by expectation onto a subspace of the conditions. Now, if we generalize more the law of three normals, the conditional expectation under the sub-history of the conditional expectation of the full history up to t, here t is posterior to s, is nothing but the conditional expectation of the same variable z under the condition of the partial history up to only s. So this is the Tower rule, the type of the Tower rule identity. Now, if we interpret in the above equation the conditional expectation up to s as a random variable ys as a stochastic process, then the above equation can be written in this form, which is nothing but the definition of Martingale. So this ys by the Tower rule is a Martingale by the Tower rule. Now, let us forget for the moment about the Martingale, and I'd like to describe what we call progressive quenching. The original motivation of progressive quenching is to study the effect of the repartition between the system and external system. So the repartition of the system and heat bath has been a lot studied in the past, about 20 years, like coarse graining and hidden Markovian, etc. However, the effect of repartition between external system and system has a little been studied. That's why we took this example. But by chance, we encountered the new type of Martingale. So our model is very simple, consisting of the Ising spins on a complete network of N0 sites. And each pair of the spins, Ising spins, are connected by the ferromagnetic coupling, homogeneous ferromagnetic coupling. Here, the N0 in the denominator is necessary to achieve the system extensive in some dynamic sense. And hereafter, I fixed the temperature always. So I absorb the beta or inverse KBT in a unity as a unity to renormalize the other constant. In this unit, the coupling J equal to 1 is a mean field critical point for the infinite system. However, we study the finite system and we prepare the system initially at equilibrium. Now, the protocol of progressive quenching is as follows. Suppose we have already 3 fixed spins, which are in blue, and the other green spins, which are thermally fluctuating. So the fixed spins plays a role of external system, and unfixed spin plays a role of system in this case. Now, after re-equilibrating the fluctuating unfixed spin, we randomly choose one of those fluctuating spin and quench at the state which it take at that moment. And then I re-equilibrate the remaining fluctuating spins, and I repeat the same protocol until all the spins has been quenched. So this is a progressive quenching. The progressive quenching can be used a crude caricature of public opinion before a referendum. So the voters are connected through the social media, and some of the voters may make up their mind either yes or no at the early stage, and they influence through the social media on the other participants. And gradually, they make up their mind until the vote is done. So we may, for example, ask them what is the importance of the initial stages and those who make a decision very early, etc. Now I'd like to introduce several key parameters. Let the capital T is a number of fixed spins that may play the role of discrete time. And by capital M T, the total magnetization of T fixed spins. So this MT obeys the Markovian evolution in our model. Then the SI is the ith spin to be fixed in this order. Now the S sub T plus 1 is the next spin to be fixed. So by this spin, if I take the ensemble average given the external field or the total magnetization up to stage T, this is MT, lowercase small mt, which I call the equilibrium average of the spin under the given external total frozen magnetization. So this MT plays a role of Y, while the previous total magnetization plays a role of X. Now, once we know the small MT, the next spin to be fixed takes the value plus 1 and minus 1 at the probability respectively like this, 1 plus MT over 2 or 1 minus MT over 2. Now, the argument is the following. So by definition, MT is the expectation of the next spin to be fixed. But by the homogeneity of the complete lattice, we can replace this spin by the last spin to be fixed at the final stage. So we can keep always the same index here. And then I could add, in addition to the condition MT, all the past history. In fact, it makes no change because the MT evolves in the Markovian sense, so the value is the same. But now the key point is, if we can regard this conditional probability with history as what we have in the general definition of Martingale by Tower rule, we find that MT is Martingale. In fact, this Martingality is verified by our numerical calculations. So we claim that the MT is a Martingale hidden behind the frozen magnetization, which is a principal process, stochastic and Markovian process. So its consequence can be seen most conveniently by using the Dove-Meyer, so-called Dove-Meyer decomposition. So the increment of the frozen magnetization is a spin to be fixed at the last time. And we decompose this into the mean value and the fluctuation around the mean, where mean has been just defined. So this is the mean value, mean drift term, which is Martingale. In analogy to the stochastic differential equation of Ito type, in SDE, it is the drift velocity term, which is Martingale. Now, if we make the sum of all the consecutive steps of the Dürr-Meyer decomposition from T to the last spin to fix, on the right-hand side, we have the hidden Martingale term and the noise whose average is 0. So if I take really the conditional average given the history up to T, we find this equation. So this equation connects the expectation value of the last frozen magnetization as a function of MT at the frozen magnetization at the intermediate stage. So the analogy to the SDEs is like this. So this equation with shaded in pink can be used to infer the intermediate value from the final observation of the average expectation of conditional expectation of the frozen magnetization. So this is a type of usual usage of the Martingale as an expectation. But today I'd like to tell you about 3 examples in which the Martingale is used in a conventional way, in an unconventional way. The first is the geometric optics approximation, and the second, local invariance of the path rate, and the reversibility between the progressive quenching and recycling in some submanifold. So the first outcome of our Martingale is an approximate prediction of the final probability distribution of the frozen magnetization given the data of the early distribution. So these curves on the left shows the evolution of the probability distribution of the frozen magnetization as with the parameter T, which is the number of quenched spins. So in the early stages of the progressive quenching, say 16 spin and 22 spin, etc., the distribution is single peaked or monomodal, but in the later stages, the peak splits into 2 and the curve is bimodal. And finally, for 512 spins, we have this bimodal distribution. Now, we took the M0 as the 512, and I forgot to say, sorry. And the coupling it has been chosen to a kind of critical point in which the response of the system is the largest. Now, if we started the progressive quenching with no biased field and up to the 16 spins quenched already, we have this curve with 17 data points. Now, if we use the Martingale property in a way that I explain in the next slide, we can predict the final distribution, which is bimodal, with shown with a dense dot, with only the 17 data points. And if we started from a single spin, which is surely up, and continue to freeze the other 15 spins up to t equals 16, the prediction becomes like this. It's quite pretty well reproduces the bimodality and also the asymmetry. So the idea to predict the final distribution of the frozen magnetization is the following. So we have already know the exact relation between the intermediate value of frozen magnetization and the final expectation. However, even without expectation on the left-hand side, we may expect that the relation between the intermediate value and final value is approximately like this if we can ignore the seemingly less dominant part, which is average 0. So this is a kind of the spirit of geometrical optical approximation with respect to the wave optics. So if we use this and ignore this fluctuating term, the rays can carry the probability of the early stages to the final stage using this approximation or this formula, and the result works pretty well, like this. Now, the second outcome of our martingale is the local invariance of the path weight. So all what we use here is first the fact that the spin are easing, taking only plus and minus 1, and the frozen magnetization evolves with Markovian process, and the unfrozen mean spin, equilibrium value of spin, obeys the martingale. Now, if I apply the martingale property or definition for a single step of the quenching, so t plus 1 from t, the concrete form of this expectation can be written in terms of this, where the fraction is the probability and the factor is the value that it takes, and the right-hand side is copied. But using a simple algebraic identity among A, B, and C, we can rewrite this martingale statement in this form. Now, this form tells that kind of local invariance of path probability. So in the plane of the total frozen magnetization versus the number of frozen spins, the sequence of fixing the up spin, then down spin has the same probability for the fixing minus spin and then up plus 1 spin. So this causes the degeneracy of path weight from a given point to the final point. For example, if we are given a trajectory of the total frozen magnetization as a function of the number of fixed spins, like this in green, thick line, we can apply the local invariance consecutively until the path becomes all quenching the down spin before quenching the up spins. By doing so, the path weight can be represented by the representative path like this, which can be written in this form. And we can associate or define the energy function, which is a function of only the endpoint, by this formula. By the way, the number of different paths gives just the degeneracy, due to the degeneracy, just a combinatorial factor, by which we define the entropy, which is function of the two endpoints. So by combining these two, we find the probability to reach this point at the stage t, pm colon semicolon t, in the form of the Boltzmann factor or canonical form. And we verified directly that this form is correct. So the last example or consequences of our martingale, which is unconventional way, is a reversibility between the progressive quenching and what we call recycling. So while the progressive quenching stocks non-volatile memory, because we fix the spin forever, the recycling releases the memory. So for example, among the blue fixed spins, we randomly choose one spin and release this fixation. So now this spin is fluctuating thermally. Then we again, okay, now we call this operation the recycling and associate the notation capital R. And then we randomly choose one of the spin and fix de nouveau. So this process is just a quench which we have already used, and we associated the notation capital Q. So we alternately applied R and Q and repeatedly, and we consider how the distribution evolves. So in this sense, R and Q are at the ensemble level, the transfer matrix. So by this operation, which is repeated infinitely many times, we can define the two fixed points or fixed distribution. One, which we call P star sub QR, is a fixed point for the operation of Q after R, recycling. And the other, which we call P star RQ, is the fixed points after the operation of recycling after quenching. Or in other words, these are two eigenfunctions, left and right, which are usually generically different from one to the other. However, if we notice the Martingale property or local invariance, which is equivalent of mean non-equilibrium spin, we can show that these two equations for eigenfunctions are equivalent. So therefore, the solution is unique, the same. And moreover, we can show that this unique solution is nothing but the probability distribution of the progressive quenching, which we have discussed, starting from the unbiased initial condition. We have verified this numerically also. Now, if we have started from arbitrary number of fixed spins and arbitrary given the probability distribution of the frozen magnetization, the distribution after the infinite repetition of alternative application of recycling and quenching brings the distribution to the one of the distribution function of the progressive quenching. So in this sense, this series plays a role of center manifold, and on this center manifold, the recycling and quenching is mutually the inverse operation. So these are what we have found up to this point. So in summary, we introduced the progressive quenching of spins, and we found, in fact, by chance, that the mean equilibrium spin is a M0 to T Martingale hidden behind this Markovian process. And we explained the three unconventional aspects of Martingale beyond the simple use of expectations. So the geometric approximations to predict the distribution and the local invariance to construct the canonical probability distribution function, and the reversibility of progressive quenching and recycling. All these have been verified numerically. Yet there is something which we are just started to understand slowly, and the ongoing question is first, how can we identify this mean equilibrium spin, which is given in this definition with equality, with the generic expression of tower role Martingale object. And second is, how can the Martingale of this MT generates a Boltzmann weight like a canonical distribution? Because in general, the Martingale has nothing to do with the equilibrium distribution, and even the Markovian distribution process. And our understanding up to this point is that there must be some underlying extended canonical structure for the hybrid state space of fluctuating spin and frozen spins at any stages, which is mentioned briefly in noted added in proof, and details are in preparation. Thank you very much for your attention.
Thank you very much. So now it's time for questions and comments. You can raise your hand or you can unmute yourself. Yes, please.
Yeah, so shall I? Okay.
Yeah.
So I have a question. So do you need this all-to-all coupling to ensure that you have this, somewhere you use this property of homogeneity. So for that you need this all-to-all coupling, or is there a reason for use this all-to-all coupling system?
Okay, in order to have homogeneity, I have to have the complete lattice.
Okay, okay, I see.
Yes.
So can you do it with also a periodic boundary condition, like in nearest neighbor coupling, but then periodic boundary condition?
Okay, before we have studied a different system which is quasi one-dimensional, and we quenched from one side to the other.
Okay.
Yes.
I see.
We haven't studied at that time the Martingale property. So
Okay.
yes, but progressive quenching is well defined in that case also.
I see.
Yes. Yes.
Okay, thank you.
It's me. Thank you.
Okay, so other questions or comments? So let me ask.
Yeah, I just have maybe a naive question. So when you had this progressive quenching, so suppose I have an Ising system and so in that example, the first example you showed that you have, let's say, 3 spins which are up and then you quench progressively.
Yes.
So when I guess the final state you go to a state where basically everything is up, right? So if we have it, so initially suppose 2 kinds of spin, there's 3 spins I keep it up and then 3 spins I keep it down and then I quench it progressively. So do I go to a phase separated state where like half of the system is up and half of the system, I mean, like there'll be some Gaussian fluctuations probably, but
okay. So it depends, maybe it depends on the value of the coupling. And we have chosen the coupling J at the critical point. It means that as we progress the quenching, the coupling among the unquenched spins becomes weaker and weaker because there are less and less spins which interact actively. It means that the system becomes off critical in the paramagnetic side. So even if we started from a critical point, it is no more the critical point. On the other hand, because of the fixed spins which have some polarity by fluctuation, this has a bias on the quenching. So it is really long memory along the progressive quenching. Yeah. I don't know if I have answered you. Yeah.
Yeah, kindly, I think. But like suppose now instead of keeping only one kind of initial spins, I keep, let's say, 5 spin up and 5 spin down. I frozen with that initial state and progressively I quench it.
Yes.
So where do I end up?
Okay, so we have to repeat many times this experiment, starting from 5 up and 5 down. We have distribution. And distribution can be bimodal if we have a lot of spin to quench after 10 spins. But if we have only 15 spins, maybe the distribution is unimodal. Okay. Yeah, so this is a compromise between the fluctuation and memory. Yes.
Yeah, thank you.
Thank you for the question.
Okay, so other questions or comments? So we still have 2 minutes, I think.
Is there a specific reason why you keep saying like it's a fluctuating memory or something?
I'm sorry, I couldn't listen because of the quality of the communication. Could you repeat?
Yeah, so I was asking like, is there a reason for thinking of the spins as a part being memory? Like for example, like the spins which you are fixing, those spins are like fixed memory or something.
Sagawa-san, could you help me to?
Oh, I see.
Yeah.
Could you repeat the question? Maybe the sound was not clear, I think.
Okay, you too also. Yeah.
Yeah.
What should I? Yes.
Why? Yeah,
okay, thank you. Think spin as memory. Do I think the spin as memory? Once I fix the spin, I keep this polarity forever. So by this simple reason, I think this spin as a memory. Did I answer your question?
Is that okay?
Okay. Does it relate to computer memory? Okay. So the fixing the spin is a model of the memory. That's for sure. And here I registering the memory bit one by one in an interactive way. I don't know if I understand your question correctly, but this is what I can say for the moment. Okay, why would we have fluctuating memory? In the individual process, stochastic process, the memory don't fluctuate. But since the total magnetization of frozen spin evolves as the new spin is fixed, the value of capital M fluctuate with number of fixed spin. Okay, maybe the confusion, my way of saying is a bit confusive or misleading because I use capital T as fictive time, but this is not the real time.
Okay, so maybe it's time. So, okay, so then let's thank the speaker again.
Thank you, Chairman, also, and thank you to all.